Basically, like this week is basically just trying to catch up.
Hi everyone, I hope you all are here for the R review session. That's what I'm doing. Um, if you haven't been to one of these before, my name is Will. I'm one of the TAs, and I'm mostly going to be walking through how to do homework 5. The emphasis of this is supposed to be on like any troubleshooting you have with using R code, but using the R code and the stats is so intertwined that I'll help you out with both. So if you pay attention, we'll probably pretty much do homework 5. And I'm trying to record this time. I've got this mic here, so hopefully we'll be able to have this on YouTube or something like that, so that way you'll be able to follow if you missed anything and be able to do the homework stuff for that. So yeah, I like this to be a lot more like, it's a smaller group, so I feel like it's a lot better when you like go back and forth. So any questions you have or how to do stuff, or if you have any even trouble just running something, just let me know, and it's a lot better if it's like back and forth. That makes any sense. Okay, so have y'all started this homework, or are we pretty much starting to go from scratch? Okay, so for this homework, we're doing all the transformations, which this one's a pretty hefty one in my opinion, because these transformations, they can be kind of weird. But essentially what we're doing is you can do a lot more things with linear models than just a straight line. And the reason why you can do that is because you can transform the different variables. So you can have a log transformation or an exponential transformation or pretty much anything you can imagine. You can be creative, and you'll fit different lines to that. So this one, I don't know if you looked at the last, we worked off of the last homework 4, where we have that the diamond small. And remember, it had kind of that non-linearity at the beginning, and it was heteroscedastic as we went, bigger diamonds. So basically, we're going to try and fix those problems. And you'll see we'll be able to create a better model by using some of these transformations. Okay, so this is the homework we have right here. The homework 5, I just copied it from the Canvas site so it's easier to get to. And we're just going to go ahead and load the DA, which is the same command as last time. And so when I load it, I should see this diamonds. And like I always say, I recommend whenever you load something to look at what you just loaded. So you can look at the head command. I like the structure command because it says what type of DAB we have here and if we have observations. So if you had trouble loading, you'd be able to see it here right away, which is big. And again, you kind of see what sort of information you have. We have price, which is an integer again, caret size, which is a number. And like last time, we have 3 factors. We have color, clarity, and cut. So they're not ordered now, and we might order them later. Okay, so this is all same stuff from homework 4. Hope this is no trouble. All right, so let's get to it. In the previous homework, you created model caret, a linear model that predicted price from caret size, regenerate the model, and generate the scatter plot and the residual plot for it. Okay, so this is basically just repeating stuff you had from homework 4. It mentions here that you can add a line through the origin to your residuals with avline 0, 0. That's, I mean, all that's kind of funny to me because you can just do that right away with that plot, the name of the model command, and it'll do that for you. So I'm just going to steal some same stuff from homework 4 and just copy what I did before. Hopefully you still have your homework 4 and you're able to just copy it as well. If you'd like some help on how to do it again, I can do that, but I'm just going to copy what I did before. What's it called again? Model carets. Okay, it's not here. Okay, so I forgot what model caret is, but simply just price regress against caret size using the diamonds. And we can see the model, the summary command, to see what coefficients it finds. And you can see that we, with caret size, it increases again, and we start off with a negative price for diamonds, which doesn't make too much sense. But it grows from there. It makes sense because you can't have a 0 caret diamond. That doesn't really make sense. Okay, so if we want to plot the residuals, there's that plot residual command. But I just like plotting the model because I can remember 4 layers. Oops. And so when I do that, it'll ask me a prompt to just return. I press the first time, and you'll get what you are looking for. So here's our residuals versus FID. And what can we see that is wrong with this model? Anybody? Yeah.
It shows a fan-like pattern.
Yeah, we got fan-like pattern. You can see here that over here it's pretty narrow, and over here it's as wide as it gets. What else do we see? Curve, yeah. So that's what this red line is supposed to represent. That abline 00 command, that would build this straight line right here. And this red line is a spline that's basically just kind of like what the average is of the residuals. And ideally that would be flat, because that would mean that it's not adjusting. But so if we're trying to predict the really low cost diamond, something over here, are we going to over predict or under predict? Or are we going to hit? What does this mean?
Wouldn't we overpredict like up to a certain point, but then like after between 0 and 2000, we just tend to underpredict?
Exactly. So under 2000, we're going to tend to underpredict. And you can kind of see that because you can see the residuals are always up here. We have never predicted correctly with this model any diamonds less than, it looks like about 1,000. We always predict lower than that. So I mean, that's something to keep in mind when you're using these models, that if someone called you and asked for what around $800 diamond is, you probably would just try and buff it up a little bit because you know you're under predicting every time. Okay? So that's what we would kind of want to observe from these plots. And you can just copy this plot with copy image and paste it into your homework, like such. Okay, any questions so far? Yeah?
You mentioned the y-intercept, that it makes sense. How does it make sense even though it shows a negative number for the intercept?
Okay, so yeah, we'll demonstrate that in a second here. Let me flip through the rest of these plots because they're going to make me do it. If you wanted the second one, you see a QQ plot, which just what can you observe is not good about this one? What does this mean? What do I use this QQ plot for?
The normality assumption?
Right. And so ideally, wherever these dots would be on the line, right? So does anyone know if it's left or right skewed with this QQ plot? So I think it's actually right skewed here. And that makes sense because you'll see the big diamonds. And also because we underpredict. Okay. And then don't have to worry too much about these, but these aren't very pretty looking either. You like straight lines in all these plots, kind of thing. Okay, so you wanted to see kind of what this plot looked like, right?
No, you mentioned on the model Karat, you mentioned the intercept at negative 1,660.
Mm-hmm.
You mentioned that it makes sense. How does it make sense even though it's a negative amount?
Yeah, so it doesn't make sense in the sense that you would tell someone that you have a negatively priced diamond that you want to pay people to get rid of. It makes sense in the sense that when we see this plot, let me finish doing this. Price is a function of carat size. When we see this plot, and you kind of draw a line in your mind, like it's going to go way down here, right? So it's going to go past 0, but that's really just because it really isn't linear. You can kind of see it kind of curves up. Yeah. Okay. So yeah, I guess that shouldn't make sense. You're right. So if you want to see, I recommend doing this a lot. If you want to see your plot with the your curve, I recommend plotting your data like this. I'm going to add some labels, which you should do if you're turning in your homework. It's lab means give me a label, with my x-axis being carat size, my y label being price, in dollars. I'm gonna give it a tile 2. What is this model carrots? And then I'm going to add line, which is basically just draw the line in my regression. Okay. So now when I run these two, I get this plot here, which shows the regression line. That's kind of a nice way to see what's going on. So what else can you say is wrong about this data set? Out of curiosity. What's the max price diamond here? It's 10,000, right? And it's kind of weird how they're like all cut off at 10,000. I can tell you this line right here is 1,000, which seems pretty artificial to me. So I think you have kind of some censored data here that like there's probably some diamonds that cost more than 10,000, but some reason when they made the data set, it just like cut it off at 10,000. So you can imagine that would skew your results too, right? Like you kind of see with that heteroscedasticity that like fans out and then narrows back in with kind of an artificial cut. That's gonna mess with your results. If it wasn't like that, you can imagine it would go probably a little steeper. Yep.
So basically, like, so something wrong with this graph is basically it shows that most of the points are either below 2,000 instead of 10,000.
Yeah. So what I'm saying is that it's likely, I think, that a lot of these diamonds are actually priced less than $1,000, but we actually don't get to see them because they're just artificially raised. And then the same with these $10,000 diamonds. I really doubt there's that many diamonds that are exactly 10,000 and no diamond that's cost more than 10,000. My money's on the fact that there's probably some diamonds that are above that. And so when you censor that data, it's going to artificially flatten your slope. Okay, so any questions on how we did that or what we're doing? No? Cool. Okay. When there is a curvature present, we try transforming the x value. So we saw that curvature, that's kind of what we're mentioning. That was with the plot. You saw that it was not a straight line. We tried transforming the x value. Describe the curvature in the relationship between price and carat size, and suggest 3 possible transformations that you might try. So that's less of an R code problem and more of just from the perusal reading. It's a pretty long one, but this topic's a little bit difficult in my opinion. So it mentions a few transformations. I don't recommend just memorizing them. You kind of do them just from experience. One of them was, I don't know if you remember the reciprocal relationship. So essentially it's like you do 1 over x. Another one you can do is the log transformation. That's probably the most common one. The log is kind of the blanket one you do on everything. And then you can also try like a square root or some sort of power. So not any art code on that one, but that's kind of just more what transformations can you try. I mean, really, you can do any transformation for making a linear model, just so long that the order is kept. As long as you're not like reversing, you know, like all of a sudden this one's over here and this one's over here and it's jumbled. So long as you still have a linear transformation, that's what they call it. Yep.
Is there a way in the art studio to create a transformation based on reciprocal relationship?
Yeah, so the way you're going to do all these transformations is you're just going to artificially transform the x variable yourself. So the way I would do that here, for example, is if I were doing like a reciprocal relationship, I do the same thing in model carat. I'll call it model carat recip. And I'll make price a function of 1 divided by carat size. Or you could, I think it's easier for it to do the power of -1, which if you, that's the same thing as doing a reciprocal. And then when you run it, invalid power in formula. Didn't like that. Divided by carat size. Yeah, there we go. And let's see a summary of it. Oh, I didn't like that either. All right, so I haven't done that one in practice, but the way I guess you would have to do it is you have to go and create a new variable called 1 over caret size in your data set and then apply it on that. So I'm not going to go through the time of doing that, but you can transform it however you want and then just plot it against the new variable you created. Just like changing your units, it's nothing weird. Really, like what we're doing is the same thing as like when you have kilograms and you want to plot it against grams instead. You just divide it by 1,000. That's just a simple transformation, except we're doing a little bit more complicated than just divide by 1,000. We might take the log or something like that. It's the same thing though. Okay. Any questions? Good question though. Okay. So, would you think it's appropriate to try an exponential transformation on caret size? Why or why not? So what's the problem we have here? What's kind of the problem? It's like this stuff over here, it gets bigger, right? It's like we have heteroscedasticity, like the big ones are too big, right? So would exponential help with that? I like what you're thinking, but I don't think it does. And the reason why is because, like, if you think of it exponential, e to the power of like 100 is just gigantic, while e to the power of like 2 is not that big of a deal. Exponential, you know, it blows everything up in kind of a way. So actually, in this one, I don't think it's too bad. It wasn't a great example, but the way we're trying to teach it is that these numbers, like these numbers over here, are going to get really big, while these numbers aren't going to move at all. So we can actually test it out real quick. So I'm going to call this exp. Price is a function of exponential caret size. And they'll do it. They'll make the equation, and then when you try and see it, you'll see that it's not too great, because you can see this this pretty bad bend here. These data points are getting really thrown out because they were really big now. QQ plot, you see, is not really very normal at all anymore. I don't think it worked out very well. So I don't think exponential is a great transformation for that reason. And if you want to see kind of what I'm talking about, you can plot the two things. So all I did was exponentiate the x-axis, and you see that these numbers, which originally were over here, are all the way out here, because 2 to the power, e to the power of 2 is something like over 7. So it just spread everything out, which isn't what you're trying to do.
So instead of flattening the trend, it just makes it worse?
Yeah, so exponential, it kind of does the opposite of what we're trying to do. Exponential is spreading things out on the x-axis, which there are some applications where you might want to do that. If everything is like too condensed inside and you want to spread it out, it would work. But in this case, not so much. Okay. Flying through this. When there is significant, so finish 3. When there is significant homoscedasticity, that meant heteroscedasticity. We try transforming the y values. Describe what you're trying to do when there's a classic fan or funnel pattern in the residuals. And provide 2 mathematical transformations that might accomplish this. So if we look back at this, What are we trying to do with the y numbers? Trying to make the big ones sucked in a little bit, right? So would exponential be a good one for this one? No, for the same reason as last time, where it's going to blow out the big ones. So what's the opposite direction as exponential? Anybody? It's a lot more fun if other people talk, by the way. Yeah, square root would be great. Anything to a power of less than 1. Reciprocal? Yeah, that could work. I haven't tried that one, but that might work. There's one more I'm specifically thinking of, though. The really common. Yeah, the log. Log is kind of the go-to, in my opinion. It's kind of a nice one. So yeah, any of those I would be good. Okay. So those first 4 are mostly just talking. So now we're going to try some transformations. So the actual R part. We're going to create columns for natural log of price, called price log, and natural log of the size, and the square root of the size. So this is just basically plug in some pretty basic R stuff. So we have price log with it. Make sure I'm doing it exactly like the homework asked. Price log, no capitalized. So in the data set diamonds, I'm going to make a new column called price log that is simply the log of diamonds price. Okay. Similarly, I'm going to make a size log that is just the log of diamonds caret size. Finally, I'm going to make one for, I think they call it square root. Size square root, which is simply the square root of diamonds caret size. Okay, so hopefully that's not too bad. Just make sure you're using diamonds before each of these. And if you're using the attach function, it's a little bit weird. You have to reattach it basically because you're creating new columns. But it does work. So when I have those done, I just run them. And if you now look at your data set, you can do the view. I like the head function. You should see a new column called price log, size log, and size square root. Can you all see that? No. Yep.
How come the natural log for price has the same number for all 6 of them?
For these first 6, the price is all the same, 1,000 here. But I'm sure we have some other ones. So if I want to do a histogram of price log, you can see they definitely have some different ones here.
So it's not as different as, so it's not the same as one thing?
So yeah, it is still related to price, but it just so happened the first 6 diamonds I have here have the same price of 1,000. They're probably sorted by price if I had to guess. But if you did a view of diamonds, I don't have that downloaded. Yeah, I don't know. Don't worry about what I'm doing. I'm just trying to show you something here. 1,000. My R skills are off. There we go. Yeah, so here you can see the price is 1,001. And so it changed a little bit. It just so happened I grabbed the first ones were thumbs. Okay. So any questions on that? Just transformations real quick. So now we're going to make the actual models. And it's just a law of models here. But there is price log with caret size predicting the natural log of price. Size log with the natural log of caret size predicting price. And those are only two. So there's a lot of models in this homework. Price log. I think that's what they asked for. Model price log. And you just write like you'd write any other linear regression, linear model but this time we're going to use price log as what we're predicting is a function of caret size. So we have also size log, which is going to be the regular price as a function of size log, sorry. This variable here. And we can run those two. Okay, so this first model, we're not regressing price anymore. We're regressing the log of price. So it's a lot less intuitive to use because no one cares about, if someone asks you for the price, they don't usually ask for what's the log of the price. It's a little odd. So it's just kind of a mathematical thing we do, so that way it creates a better regression. And the reason why we have the transformation of log there is because essentially now we're doing e to the power of that stuff there. Okay, so so we just created these two models, price ln and size ln, and now we need to show your code and write out the prediction equations for model price ln and size ln. So writing out the prediction equations is an important thing to show understanding of this. So when you look at the summary of, we'll start with the easier one in my opinion, model size ln. So when you look at this, you'll see that price is a function of the log of size. So people watching this on YouTube will not be able to see me right on the board, but this rank price is equal to some intercept plus beta 1, the log of the size. So whenever you're plugging in for the prediction, you no longer plug in just size. You have to plug in the log of the size. Okay, but the output will be price in terms of dollars, which is what you're looking for usually. Okay, so that's size log. Now price log is a little bit trickier, and because what it's regressing is actually a prediction of the log of price. Regress against beta naught plus beta 1 times the size. Now you can plug in size just as the normal carets, but usually you don't care about the log of price, so you need to exponentiate both sides to get price. So you take e to the power of this and e to the power of this, and that's still equal, and so you'll get that your prediction for price is equal to e to the power of beta naught plus beta 1 size. So any prediction you make from that model, you need to exponentiate the results to get price in dollars. Because you have some weird log dollars is your units from that model, which no one uses log dollars. That make sense? That's kind of the tricky part. Yep.
So for the price, the price ln, you basically just use both the formulas or just one of them?
there's only one formula for price ln. That's this one right here. I mean, yeah, it's the same thing. It just depends. Like, usually you're trying to get a natural price, and so you'll eventually want to use this bottom one. But that's how we get to that. So the way R is working is in this top model, though. That's what R is thinking. It doesn't think in terms of exponentiating. Okay, so to write out these equations, from this model size ln, I'll kind of write it out here. The way the regression works is that it is size ln is just going to be, the price is going to be 5,057.66 plus 5080.56 times the log of caret size. That's for size ln. For price ln, we'll have the log of price is equal to 6.495 plus 1.826 times caret size. And the transformation for that will just be that the price is equal to exponentiated this. Does that make sense? Any questions on this? Yeah.
Would it work the same way using the natural log?
So these two are equivalent. Yeah.
Okay.
Just when you're answering questions, don't answer with log dollars, please. I will take off of that. Okay. Predict the average price of a 0.5 carat diamond with model price ln and model size ln. Okay, so we're doing a 0.5 carat diamond. I'll do the size ln first because I think that's the easiest one. So to get that, we can just do 5,057.66 plus 5080.56 times the log of 0.5. Okay, so that's doing it by hand, which I think is the easiest way to do it. If you want to do this with the predict, it's a little bit trickier, but you'll do predict lm, the name of the model, and then the new data set, which I have a funny way of doing that, but you need to make sure you're using the same names as here. So you can't put in carat size as your variable anymore. You need to put in size ln. And you're not going to put in 0.5. You need to put in the log of 0.5. And there's a lot of, yeah, that's right. And so we'll get the same value. About. Make sure you're doing that with the log of 0.5 if you're putting them in. Okay. For price ln, again, I can just copy this formula here. So that'd be exponential of 6.495 plus 1.826 times 0.5. Which is something around there, 1650. And if you wanted to predict it, you do it like this, but you would be using the original carat size, because carat size is not transformed, with 0.5, not the log. And, oops. Now you get 7.4, so don't turn in 7.4. What am I forgetting to do? Sorry? Not the log. You're close though. It should be a lot bigger than this, right? $7 would be a pretty cheap diamond. You need to exponentiate it. For this reason here. We were in this one, we just got the log of price from it, the prediction. So we need to do this. So if we run that, that comes out to be the same number as what we got from plugging in by hand. Okay. Any questions on that? Yep.
So it's using the same one, but just put the exponential in the front.
Yeah, it's similar concept. It's just the y variable was transformed in the price ln, so you have to transform the prediction that you created essentially. It's like you get the prediction, but the prediction's for some transformed y variable, which no one works in log prices, so you need to switch log prices back to regular prices. Okay. So that's predicting the average price. And make sure you note that this average price is not just the price for a 0.5 carat diamond. So now we have to create two more models, log square root and log log, with the square root of carat size predicting the natural price of log. All right. You just kind of notice that the way it works is the first one is what the y variable is transformed, the second one is what the x variable is transformed. So I'm going to copy those two models, names. And so this log square root is equal to, similar to what we did here. I'll type it out. It's easier for you. A linear model where we're predicting the price log as a function of size square root that equals diamonds, and this one pretty much the same thing, price log is a function of size ln. Okay. Okay, so when we're working with these, it's kind of like we did both transformations now. So you gotta plug in your x's in terms of its transformed version, and then when you get the prediction, you have to transform that back into real dollars. Any questions on that? So when we run those, again, I'll put the summaries. For log square root, we see that for each square root of a carat, we increase the log of the price 3.4. So it's starting to be so out there that you can't really make sense of it by just like looking at these things, but you can tell that it's still increasing with diamonds. So the way we write this out, like I said, is that the log of price is equal to 4.968 plus 3.401 times the square root of carat size. Equivalently, that would be that price is equal to the exponent of all that. That transformation, I hope you all get that transformation pretty quick. That to get rid of the log, you just exponentiate both sides. This will be really common. Same thing here. So for log log, we see that for you start with 8.404 log dollars, and we increase 1.500 log dollars for each log caret. It's all gibberish to me, but we write out the formula again. And I can transform it by just getting rid of the log on the left and exponentiating everything here on the right. Okay, any questions on that? Hopefully it's starting to seem repetitious. Okay, predict the average price of a 0.5 carat diamond with model log square root and model log log. I'm not going to do that for you guys because you'll kind of seen how to do it here. I'm trying to realizing that I'm running out of time. But again, you can just plug it into this equation you just wrote, or you can do the predict and make sure you're plugging in the right units in terms of if you're plugging in square root carat size or log carat size. And for both of these, you would exponentiate the result. Okay. So that's number 9 and 10. Using log log, how much more would an average 1.5 carat diamond cost than an average 0.5 carat diamond cost? Now, and it says, does this number look familiar? It's not going to be very intuitive about why it is, but so you can just do it by hand. And if you do it by hand, let me kind of write this out. But the so using this. So the log price of a 1.5 would be this, right? And I'm going to divide this, it'll make sense in a second why, by the log of a 0.5. And that would be the amount that, and so if you're used to your rules of logs, what that is that the log of something divided by the log of something is the same as the log of that minus something inside the log. So what I just said is 1.5 minus 0.5 is equal to this above. These two are equivalent. And so, yeah, so that's going to be this from before times this after. So it's probably easiest just to do this by hand, but the way it works out is that the coefficients of the two, it just multiplied by, how do you say it? It's the log of, I'll do it by hand. Yeah. Sorry, I'm gibbering. 8.405 plus 1.5. 1 plus the log of 5. So that's the price of the 1.5 carat diamond, and this is the price of the 0.5 carat diamond. And if we look at the how many times bigger that is, it's 8. This divided by that, right? And it's 5.196. And so the way we get to that is it's exponential. It's 3 times bigger. Times the log of the coefficient. 507. Oops, did not do that right. Let me check my cheat sheet here. There we go. So you see here that the log of the price difference is equal to the log of the price. So subtracting each other. And so you can just do the beta naught minus beta 1 log 1.5 minus beta naught plus beta 1 log 0.5. And so you just end up doing beta 1 times the log of the multiplication. So that would be beta 1, which is 1.5001 times the log of 1.5 divided by 0.5. Which is still not working out. Oh, I need to exponentiate that still. There we go, 5.19, which is the same as what we got when we divided it by the 2. So this formula, I know I'm dropping a lot here. It's the same as 1.5001 times 3. No, it's not. All right, I can't do it today, but there's a quick key doing that, which would be good if you remember it, but obviously I don't remember it either. So, all right. There might be a lot of questions on that, but I can't answer them right now, so we'll move on. So you can do it just by hand by just plugging in the formulas. So as long as you get how many times it's going to be over this one, you'll be fine. Okay, so which of the 5 models that you created is the best? And you need to have some sort of support about why it is. So it's really kind of tough to just pick which one is the best outright. I have some code written about how to do this where you can see them all graphed. That's kind of nice. Let me pull it out here. There we go. And so you have to transform each of these to be able to like see them, but I'm just going to try to do it graphically. It's kind of cheating for you guys, but come to me. There we go. So what you're doing with all these transformations is actually you're like, this blue line is your linear. There's a key. Hold up. Why is it so big? I don't know why that key's so big. Okay. So what's going on is you'll see that if you transformed all these back using the curve, so you can't just do abline, you have to do like a curve and plug in the actual equation. You'll see that these are all these different transformations that you're making. So like this blue line would be the linear fit, which is what you originally had. And did anyone guess what this green line is? It's the square root of x. And you see because it kind of fits like a square root function. Yeah, and so this one might be the exponentiated version where it's the log of y. I mean, but essentially that's what we're doing with all these different transformations, that instead of just having like a linear fit, we can make these curves. Okay? And so ideally you'd make the curve that best fits how the data is going. So from this, can someone like kind of pick which one they think is the best? It's still pretty tough, right? You kind of just go with one that you kind of feel like is your gut. I personally like, I think this purple line is probably one of my favorites. But I'm willing to take any one that you go with. I don't think this green line is a very good fit. I think that kind of goes the opposite direction of what you want. I think all these are improvement over the linear fit, but yeah, my opinion is the yellow one. So it's kind of like how you would do it graphically, or else you could plot the residuals to kind of see that. So you can just go through each of these different regressions yourself and plot the model LLN. and see the residuals versus fit. So this one's a little bit ugly because this line here, but you can kind of go through the models and pick which one you like the best. Yep.
On the what does the yellow line represent again?
The yellow line?
Yeah, the one that compared to the other 3 lines.
Oh, when I had the whole fit up. Yellow is log price and size, so the log-log relationship. Yeah, yellow is log-log. So I think log-log is probably the best. Yeah, and the numerical way of doing this is probably you want to reduce your R squared, but it's a little bit tricky when you have all these transformations, so it's kind of up to how you want to do it. Have you all heard of AIC yet? Have you all been taught that? No? AIC is a good way of checking, or else you can use the ANOVA command and then just put all the names of your models in. So, for example, we have model, and oh wait, that's not going to work. I'll take it back. ANOVA's not going to work for you guys. So you can just kind of go off of the R squared too about which one you think is the best. Okay. Calculate a 95% confidence interval for the average price of a 0.5 using model caret and model ln. So to do those confidence intervals, again, you probably want to use these predict, and this one's the ln. Wait, no, I don't have ln. So I'm going to copy this code here. And what you want to do is predict the linear model, and you want to use the ln as your model, and make sure you're plugging in size ln as your variable. And we are doing a confidence or a prediction, I forget. Someone tell me.
It's confidence.
Confidence? And so I run this. These numbers, again, they look very small. That's a very low cost diamond. And the reason why is because, again, you need to exponentiate. And please be careful when you're doing these confidence intervals. I have a lot of people that pick up the fit as their lower value. It's the middle value. I know it's a little odd, but they put the lower value in the middle and then the upper value in the right. So you have to exponentiate these, which you don't have to do them each by hand. You can just do exponential, all that, and I'll give it to you in this version. So whenever you're doing confidence intervals, make sure you transform it back, because we care about real dollars, not log dollars. Okay, and so we can see the predict from model caret. Size 5. Y'all did this before in the previous homework, but basically just doing the confidence interval of the previous one. And you'll see that it has a fit over here. And you can see that the confidence interval is a little wider for the linear fit. Any questions with that? So the confidence intervals aren't going to be flat after you make the transformation, because you can kind of imagine that it's not going to be a linear distance. So if this distance is, for the linear one, it's always going to be the same no matter where you are. It'll be the same thing because you're homoscedastic. But if you transform your y variable, like the exponential of the big value, you're going to be getting a lot bigger. So at the high price diamonds, the log ones, it's going to give you a wide confidence interval. Yeah, because you're exponentiating it. Okay. All right. So notice the interval is smaller for model ln ln. That's because we're doing very small caret diamonds here. So taking exponential of 0.5 is going to be very narrow in the beginning, and it's going to be really wide on the right side. Okay. All right. So any questions with that so far? Yeah.
So basically, the reason why it's wider than model ln is it basically because is what you mentioned before, that the larger the number just spreads out more than the smaller numbers?
Yes. So because of the big number, the high number is going to get blown up when you exponentiate it. But in this case, we're working with the small numbers, so we're doing 0.5. Okay, so next we're going to do a model of categorical variables. So we're going to do some fun interactions. So model transforms interact is now a linear model predicting, are we doing relative price here, or are we doing price ln? Price ln as a function of size ln interacted with color. And notice you don't have to do the adding. Whenever you do an interaction, it'll always include the lower terms. So we run this, and we look at it. You'll get a huge chart, which we should see 7 for colors and 7 for the interactions, because we have 8 colors, and so we'll have 7 dummy variables. Okay, and we know these are significant because we can see that there are some stars, and they're less than 0.05. Yeah, so it's just like we made that previous model, but now we made it one for each of the colors. That's what we basically just did. And if you see color LL, color Q, color C, instead of color E, F, G, H, I, J, K, what it's trying to do is it's making some sort of linear transformation, and you need to unorder your colors, essentially. So your colors are ordered, and for some reason it does some weird things when you have them ordered. And so you can unorder your colors by doing diamonds color, and you want to make a factor which is the same as what it was before, except ordered should be equal to false. And so I don't need to run that, mine's working fine, but if you see LQ to the power of 3 to the power of 4 to the power of 5, you should do that, and then rerun them all, and it'll work fine. Okay, so we have our model, and then provide your code in the summary output. Use model transform interact to calculate both a 95% confidence interval and 95% prediction interval for 1 carat color F diamond. So that's like what we did before, but we're going to exponentiate our prediction because we're doing the log of price. So I'm just copying what I had code before. We're using model transform interact. We need to do size ln of log 0.5 and color equals, was it F we're doing? Diamond's F. Diamond F. And so we run that, and we'll get our confidence interval for a 1 carat, that's 0.5 carat. For a 1 carat color F diamond, this would be our confidence interval. Make sure you're exponentiating results. It's kind of good to know what your data is, because if you ever get $7 diamonds, you know you probably need to exponentiate something. Okay. Any questions for that? Yep.
So we would do the same thing with the prediction interval, except just put down interval prediction.
Exactly. So I can just do the same thing and then prediction for the prediction interval. And if you ever forget that, remember there's question mark predict.lm, and that will remind you that your inputs includes one term that can be interval equals, and you have a choice of no prediction interval, which is the default, a confidence interval, and a prediction. So if you ever forget what things are called, that's that. Cool. So yeah, you're pretty much done. The last one is a little bit more just play with it. Create a model called model best using caret size, clarity, color, and cut to predict price. And you should experiment with different transformations and interactions. So model best, you can start with just putting everything in there. We can do price ln as a function of, we know this is good, size ln times color, plus, what's the other, what else we have here? Clarity, cut, that's capital, clarity, cut, and we can try that out and see how we did. Oops. Didn't I just run this? Oh. And you'll get a bunch of variables, which we see that pretty much everything worked out here, and we have an R squared of 0.9645. It's pretty good. And that'll do you. I mean, you can throw in as many if you want, and you can play with doing different things, like you can interact size with the clarity, you can interact size with the cut. Yeah, that'll cover it. Do I have any questions? I think that covers the homework. Yeah.
Why do you use a natural log of price instead of just price? Oh, okay. Oh, yeah, sorry.
You can do it with price, so you can see how good your R squared comes out. But we've kind of found that that log-log transformation was probably the best with this data. So I'm just sticking with that. You probably can get a pretty good R squared with a linear model, but this exponentiated model, I think, is coming out really well. Yep. Okay, that concludes it. If you want to get really fancy, you can find the actual best by I'm cheating. Interacting all these, and then that'll be a huge model, which won't be as good, but then the step function will cut down one by one to get to your actual best model. And so if you look at my it's a huge model now, but my R squared's 0.9728, which I challenge anyone to beat that, but no. Just for fun. Good. Any questions on homework or stats? R. Wow, was I not recording the whole time? Oops. Yeah.
Oh.
Glad y'all are here. I thought I pushed it. Did I push record? Oh wait, yeah, I was. We're good. All right.